NENOMATICA, where mathematics meets YouTube excellence. Welcome to our math video. Today we're going to solve a problem involving proving inequalities with radicals. Let's start by looking at our problem. We need to prove the inequality. The fourth root of 43 is less than the cube root of 3 plus the cube root of 9, which is less than the fourth root of 49. Notice that this is a double inequality with three parts that we need to verify. Let's follow the solution approach shown in the example. We'll start by defining x equals the cube root of 3 plus the cube root of 9. Note that the cube root of 9 equals the cube root of 3 squared, which is the cube root of 3 to the power of 2. Following the approach in the solution, we need to compute x cubed. If x equals the cube root of 3 plus the cube root of 9, then x cubed equals the cube of this expression. When we cube a binomial, we get a formula with four terms: the cube of the first term, plus 3 times the square of the first term times the second term, plus 3 times the first term times the square of the second term, plus the cube of the second term. Now, let's simplify each term. The cube of cube root of 3 is simply 3. Next, 3 times the square of cube root of 3 times the cube root of 9 equals 3 times the cube root of 3 squared times the cube root of 3 squared, which gives us 3 times the cube root of 3 to the power of 2 times the cube root of 9. For the third term, 3 times cube root of 3 times the square of cube root of 9 equals 3 times cube root of 3 times the cube root of 9 squared. Finally, the cube of cube root of 9 equals 9. Let's continue simplifying. Note that 3 squared times 9 equals 3 squared times 3 squared, which is 3 to the power of 4. Similarly, 3 times 9 squared equals 3 times 3 to the power of 4, which is 3 to the power of 5. Now we can compute the cube roots. The cube root of 3 to the fourth power is 3 to the 4/3 power, and the cube root of 3 to the fifth power is 3 to the 5/3 power. Let's compute these powers. 3 to the 4/3 power equals 3 times 3 to the 1/3 power, which is 3 times the cube root of 3. Similarly, 3 to the 5/3 power equals 3 to the 4/3 power times 3 to the 1/3 power, which equals 3 times cube root of 3 squared. Now, let's substitute these values back into our expression for x cubed. We get x cubed equals 3 plus 3 times cube root of 3 plus 3 times cube root of 3 squared plus 9. Simplifying, we get 3 plus 9 times cube root of 3 plus 9 times cube root of 3 squared plus 9, which equals 12 plus 9 times cube root of 3 plus 9 times cube root of 3 squared. Let's continue following the solution approach. Looking at the last two terms, we can factor out 9 from both of them. This gives us x cubed equals 12 plus 9 times the quantity cube root of 3 plus cube root of 3 squared. But remember that x equals cube root of 3 plus cube root of 9, and cube root of 9 equals cube root of 3 squared. So the expression in parentheses is exactly x. Now we can rearrange to get our equation in standard form. Subtracting 9x from both sides, we get x cubed minus 9x equals 12. Subtracting 12 from both sides, we get x cubed minus 9x minus 12 equals 0. This is now in the form of a cubic polynomial equation, x cubed minus 9x minus 12 equals 0. Now, we know that x equals cube root of 3 plus cube root of 9 is a root of this equation. Let's define a function f of x equals x cubed minus 9x minus 12. The solution shows that the real root of this equation is precisely our middle term x equals cube root of 3 plus cube root of 9. This will be the key to proving our inequality. Now, let's follow the solution and rewrite our function f of x in a different form. We can factor it as x times the quantity x squared minus 9 minus 12. This gives us a new perspective on our function. According to the intermediate value theorem, if f is continuous and f of a and f of b have opposite signs, then there's a value c between a and b where f of c equals 0. The solution notes that if x is greater than 3, the function f is increasing. This is where we'll use the intermediate value theorem to prove our inequality. Let's compute f at the endpoints of our inequality. First, let's calculate f of the fourth root of 43. The solution shows that f of the fourth root of 43 is negative. Similarly, when we calculate f of the fourth root of 49, we get a positive value. Now we can apply the intermediate value theorem. Since f of fourth root of 43 is negative and f of fourth root of 49 is positive by the intermediate value theorem, there exists a value c between fourth root of 43 and fourth root of 49, where f of c equals 0. But we already know that cube root of 3 plus cube root of 9 is a root of f. Since f is strictly increasing for x greater than 3, and both fourth root of 43 and fourth root of 49 are greater than 3, this root must be unique in this interval. Therefore, by the intermediate value theorem and the fact that f is strictly increasing for x greater than 3, we can conclude that the fourth root of 43 is less than the cube root of 3 plus the cube root of 9, which is less than the fourth root of 49. This proves our original inequality. Welcome to this math tutorial. Today, we'll prove the inequality shown on screen. This inequality involves a sum of fractions on the left side and a single fraction on the right side. Let's start by expanding our inequality to include all terms explicitly. We'll write out the full expansion of the left-hand side, starting with 1 over n plus 1, then 1 over n plus 2, and continuing the pattern until we reach the term 1 over 3n plus 1. Now, let's rearrange these terms more systematically. We'll group them based on their denominators, starting with the terms from n plus 1 to n plus n, followed by terms from 2n plus 1 to 2n plus n, and ending with the term 3n plus 1. Let's group these fractions into pairs in a clever way that will help us with our proof. We'll pair the first fraction 1 over n plus 1 with the last fraction 1 over 3n plus 1. Then we'll pair 1 over n plus 2 with 1 over 3n and continue this pairing pattern. For each pair of fractions, we'll find a common denominator to combine them. Let's take the first pair as an example. For 1 over n plus 1 over 3n plus 1, we can find that the common denominator is the product of the two denominators, which is n plus 1 times 3n plus 1. Using the same approach for all pairs, we find that each pair simplifies to a fraction with numerator 4n plus 2. For example, the second pair becomes 4n plus 2 over the product of n plus 2 and 3n. Now we can factor out the common numerator, 4n plus 2, from all the paired fractions. This gives us 4n plus 2 multiplied by a sum of fractions with different denominators. To complete our proof, we need to show that this expression is greater than 1 over 2n plus 1. Let's focus on the right side of our inequality. We can rewrite 1 over 2n plus 1 as 4n plus 2 over 4 times 2n plus 1 squared. The key observation is that the sum inside the brackets is greater than 1 over 2 times 2n plus 1 squared. This is because each term in the sum contributes positively, and the sum of these positive terms exceeds the single term 1 over 2 times 2n plus 1 squared. Therefore, we have proven that the sum of fractions 1 over n plus 1 over n plus 2 plus plus 1 over 3n plus 1 is indeed greater than 1 over 2n plus 1. This completes our proof of the inequality. Today, we'll solve an interesting inequality problem involving a product of fractions. Let's take a look at our example. Here's our problem. We need to verify the inequality 1/2 times 3/4 times 5/6 times 99 over 100 is less than 1/10. Let's first understand the pattern in our product. We have a series of fractions, 1/2, 3/4, 5/6, and so on, ending with 99 over 100. If we observe carefully, we can see that for each fraction in our sequence, the numerator is always 1 less than the denominator, and the denominators increase by 1 each time, starting from 2 and ending at 100. Now, let's establish some key inequalities that will help us solve this problem. First, let's compare 1/2 with 2/3. Next, let's compare 3/4 with 4/5. Then, let's compare 5/6 with 6/7. We can see a pattern emerging in these inequalities. In general, we can state that for any integer n greater than or equal to 2, n minus 1 over n is less than n over n plus 1. This gives us a sequence of inequalities. 1/2 is less than 2/3, 3/4 is less than 4/5, 5/6 is less than 6/7, and so on. Finally, 99 over 100 is less than 100 over 101. Now for the key step. We can multiply all these inequalities together. This means the left side will be 1/2 times 3/4 times 5/6, and so on until 99 over 100, which is exactly the product we're trying to evaluate. On the right side, we'll have 2/3 times 4/5 times 6/7, and so on until 100 over 101. Now, let's simplify the right side of our inequality. The product on the right side can be written as 2 over 3 times 4 over 5 times 6 over 7, and so on. Let's substitute x for our original product. That is 1/2 times 3/4 times 5/6, and so on until 99 over 100. Let's define a new relationship. If we look at the reciprocal of x, which is 1 over x, we can express it as 2 over 1 times 4 over 3 times 6 over 5, and so on until 100 over 99. Now, let's analyze the relationship between 1 over x and the right side of our original inequality. First, let's multiply 1 over x by 99 over 100. The result simplifies to 2 over 3 times 4 over 5 times 6 over 7, and so on until 100 over 101. From our previous steps, we know that x is less than 2/3 times 4/5 times 6/7, and so on until 100 over 101. And we just found that this product equals 1 over x times 99 over 100. Now, let's multiply both sides of the inequality by x. Since x is positive, as it's a product of positive fractions, the inequality direction remains the same. This gives us x squared is less than 99 over 100. Now, we'll take the square root of both sides of our inequality. Since the square root function is increasing, the inequality direction doesn't change. This gives us x is less than the square root of 99 over 100. Let's evaluate the square root of 99 over 100. The square root of 99 over 100 equals 99 over 10, which is less than 1/10. Therefore, we've proven that 1/2 times 3/4 times 5/6 times 99 over 100 is less than 1/10. Let's summarize what we've learned. Welcome to our mathematics tutorial. Today, we'll solve a system of inequalities by following a step-by-step approach. Let's start with our example. We need to prove the following inequality. Y is less than the fraction ax plus by over a plus b, which is less than x, where y is less than x, 0 is less than b, which is less than a. We'll start by proving the first inequality. Y is less than the fraction ax plus by over a plus b. First, let's subtract y from both sides of the inequality. Next, let's simplify the numerator on the right side. We expand x times a plus b to get ax plus bx. Then we subtract ax plus by, giving us ax plus bx minus ax minus by. Now, we can simplify further. The ax terms cancel out, leaving us with bx minus by in the numerator. Factor out b from the numerator to get b times x minus y over a plus b. This is marked as equation 1 in our reference. Now, we need to show that this expression is greater than 0 to prove our first inequality. We know from our given conditions that x is greater than y. This means x minus y is greater than 0. Now, since b is greater than 0 and a plus b is greater than 0, and x minus y is greater than 0, the fraction b times x minus y over a plus b must be greater than 0. Therefore, from equation 1, x minus ax plus by over a plus b is greater than 0, which means ax plus by over a plus b is less than x. Now let's prove the second inequality, that the fraction ax plus by over a plus b is greater than y. Similar to before, we'll subtract y from both sides and simplify. We expand y times a plus b to get a y plus by. Then we subtract ax plus by, giving us a y plus b y minus ax minus by. The by terms cancel out, giving us a y plus b y minus ax minus by. The by terms cancel out, leaving us with a y minus ax in the numerator. Factor out a from the numerator to get a times y minus x over a plus b. This is marked as equation 2 in our reference. We need to determine the sign of this expression. Since we're given that y is less than x, we know that y minus x is less than 0. Now, since there is greater than 0 and a plus b is greater than 0, but y minus x is less than 0, the fraction of times y minus x over a plus b must be less than 0. Therefore, from equation 2, y minus ax plus by over a plus b is less than 0, which means ax plus by over a plus b is greater than y. Combining our two results from inequalities I And 2, we have proven that y is less than the fraction ax plus by over a plus b, which is less than x. To summarize what we've done, we fraction ax plus by over a plus b, which is less than x. In this video, we'll prove a series of inequalities. Let's take a look at the problem we need to solve. Here's our example. We need to prove the following inequalities. 1 over 1 plus 2x squared is less than or equal to 1 over 1 plus x squared plus x to the fourth, which is less than or equal to 1 over 1 plus 2x cubed, where x is between 0 and 1, inclusive. First, we need to make sure our denominators are always positive, so we can safely manipulate these inequalities. Since we're given that x is between 0 and 1, let's check that 1 plus 2x cubed is positive. Now, let's prove these inequalities one at a time. We'll start with the right inequality. 1 over 1 plus x squared plus x to the fourth is less than or equal to 1 over 1 plus 2x cubed. Since both denominators are positive, if we flip the inequality, we need to flip the inequality sign as well. So we get that 1 plus 2x cubed is less than or equal to 1 plus x squared plus x to the fourth. We'll subtract 1 from both sides and move all terms to one side to isolate our expression. Now, let's factor our expression to see if we can prove it's always non-negative. We can factor out x squared from all terms to get x squared times the expression x squared minus 2x plus 1. We can factor x squared minus 2x plus 1 as x minus 1 squared. Now, is this expression always greater than or equal to 0 in our domain? Well, x squared is always non-negative for any real value of x, and x minus 1 squared is also always non-negative for any real value of x. So the product x squared times x minus 1 squared is always greater than or equal to 0. This means our inequality, I, is always satisfied for any real x, including our domain from 0 to 1. Let's now prove the left inequality. 1 over 1 plus 2x squared is less than or equal to 1 over 1 plus x squared plus x to the fourth. Similar to before, since both denominators are positive, we'll flip the inequality. So we get that 1 plus x squared plus x to the fourth is less than or equal to 1 plus 2x squared. Let's rearrange to isolate all terms on one side of the inequality. We can factor out x squared from this expression. We can further factor x squared minus 1 as x plus 1 times x minus 1. Now, let's analyze when this expression is less than or equal to 0 in our domain, where x is between 0 and 1. First, x squared is always non-negative for any real x. Second, x plus 1 is positive when x is greater than negative 1. Since our domain has x between 0 and 1, x plus 1 is always positive in our domain. Third, x minus 1 is non-positive when x is less than or equal to 1. Since our domain has x between 0 and 1, x minus 1 is always non-positive in our domain. It's always non-positive in our domain. So in our domain, we have x squared being non-negative, x plus 1 being positive, and x minus 1 being non-positive. The product of a non-negative, a positive, and a non-positive number is always non-positive. So x squared times x plus 1 times x minus 1 is less than or equal to 0 throughout our domain. This means inequality 2 is satisfied throughout our domain. Since we've proven both the left and right inequalities, we've successfully proven the full inequality. 1 over 1 plus 2x squared is less than or equal to 1 over 1 plus x squared plus x to the fourth, which is less than or equal to 1 over 1 plus 2x cubed, where x is between 0 and 1, inclusive. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.